Episode 4. 2 episodes ago we built a table of 6 memory operations against the people who decide them, and the Learn Policy column came out almost empty. Last episode we read 4 architectures and found that 3 of them have no principled way to revise anything. This episode is about the work that is trying to fill those gaps by learning the decisions instead of writing them down. It is the most technical episode of the series, and it is also the one where I most want to be careful about price, because the headline results in this literature are real and the costs behind them are not always quoted. Start with 4 cases from our claims triage agent. The customer restates their address. If the stored one came from this same session, the right action is to skip, and if it came from a file 6 months old, the right action is to update. A policy clause is quoted: skip if the store already holds the authoritative text, update and mark superseded if it holds an older version. An escalation happens: write it if it is the first of its kind, consolidate if it is the 9th. A preference is mentioned: write it if the claim settles, hold it if the claim is withdrawn. Same observation, opposite correct action, and the deciding factor is always the prior state. 2 recalls, because this episode only makes sense against them. In episode 2 we put the 6 operations against the question of who decides each one, and the Learn Policy column was nearly empty. Update and forget were the operations that stayed unowned longest. In episode 3 we put 4 architectures against their revision path, and 3 of the 4 had none at all, while the 4th paid for 1 on every single write. So this episode is about the first of those columns. And because a learned policy is a policy over edits, it turns out to be about the second one as well. Both of those findings came from looking at systems from the outside. This episode looks at what happens when someone tries to close the gap from the inside. 3 objectives. Formulate memory management as a sequential decision problem with an explicit action space, and the phrase to hold on to there is explicit, because most systems have an implicit one. Explain the credit assignment difficulty that makes learned memory policies hard, which is the single technical reason this line of work is slower than it looks like it should be. And compare rule-based, judge-based and learned control on cost and auditability, which is the practical decision you will actually face, because all 3 are viable and they fail differently. One thing I am not going to do is rank the 3 systems in this episode. They answer different questions, and the comparison that matters is against your own workload rather than against each other. Formally, this is a sequential decision problem. The state is the incoming observation or query, the candidate item, the remaining budget and the current contents of the store. The action is an edit to that store, and the entire design question of this episode is which edits are in the set. The reward is whether some later answer turned out to be right. Read that third band again, because the asymmetry in it drives everything that follows. You act on memory, and you are graded on answers. Nothing in the loop ever tells you directly that a particular write was a good write. That single asymmetry is why this problem is harder than it looks written down, and it is the subject of the next 2 slides. Here is that set drawn out. 1 store state on the left, and every legal edit fanning out from it: write, skip, rewrite, evict, merge, promote, demote. The fan repeats, because a session is a sequence of these, and one path through it highlights as a trace trajectory. The number of branches is not a fact about the world, it is a design decision, and it cuts both ways. Every action you add makes the policy more expressive and makes the credit assignment harder, because there are more ways to have arrived at the same store and only one reward at the end to explain all of them. 7 actions is already enough to make exhaustive exploration impossible over a session. Now line that action space up against the 6 operations from episode 2, because if we do not do this explicitly the series contradicts itself. Write maps to write, and so does skip. Skip is just the null write. Rewrite is update. Evict is forget. Merge is consolidate. Promote and demote change addressing priority, so they land on index. And then look at what has nothing arriving. Retrieve is not an action in this space at all, these are right-side control policies. Index receives only promote and demote, which reorder what already exists without ever building the structure. Hold that thought until slide 19. If you take one slide from this episode into a design review, take this one, because it is the vocabulary check nobody performs. This is the difficulty, and it is worth 20 seconds of your attention. A question at session 7 is answered correctly. The right that made that possible happened at session 2. In between sit every other right, every eviction, every merge the policy made, and any of them could have been the one that mattered. The reward is a single number arriving at session 7, and it has to explain all of it. That is the technical reason this line of work moves more slowly than the architecture papers do. It is not a shortage of ideas, it is a shortage of signal. And notice that the picture would be identical if the answer at session 7 had been wrong. The signal does not distinguish which right to blame. 3 things are wrong with that signal, and it is worth naming them separately. It is sparse, most rights are never read, so they generate no evidence in either direction, ever. It is delayed, the payoff crosses sessions, so the horizon over which credit has to travel is the deployment lifetime rather than an episode. And it is a proxy. Downstream answer accuracy is not memory quality, it correlates with memory quality, and those are not the same thing. Every design in the rest of this episode is a response to one of these 3, and which one it answers tells you what it is really optimizing. None of the 3 can be engineered away. They can only be traded against each other. First axis. MEM alpha learns the right side and nothing else. Its action space is exactly 3 calls, insert, update, delete, plus a whole paragraph rewrite when the target is the always in context core block. The read side is BM25 retrieval and a frozen generator, and it is frozen deliberately, so that any measured gain is attributable to the right policy alone. I want to give that full credit, it is the only design in this episode that can attribute its own results cleanly. It also means the ceiling is set by a retriever nobody optimized. And the policy optimization drops the divergence term, which is a decision to prefer exploration over staying close to the base model. The reward decomposes into 4 terms at 2 different granularities, and the decomposition is the interesting part. Correctness is measured globally, from downstream question answering over the final store, so every action in the trajectory shares that one value. Compression is also global, 1 minus memory length over input length. Tool call format and content validity are per action, did this call parse and execute, and does this edit satisfy the semantic definition of the slot it went into, judged by a separate model. And the format rewards weight is fixed rather than tuned, because a call that fails to parse writes nothing at all, so everything downstream is conditional on it. 5 configurations, and 2 findings. Remove the content reward and the result is catastrophic, the average falls to 0.543 against 0.642, because the policy never learns what a valid edit even looks like. Push the compression reward harder and you get shorter memory and worse answers, monotonically, 0.525, then 0.509. So one of these terms is load-bearing and the other is a dial with a wrong end, and neither of those facts is obvious before you run it. And now the price, which I think belongs on the same slide, 32H100S for 3 days, 205 steps, to train a 4 billion parameter write policy. Second axis takes the opposite bet. Here long-term and short-term memory management are folded into a single agent policy, and retrieval is an action like any other rather than a separate subsystem the agent calls out to. The argument for this is real, the read and write decisions are coupled, because what is worth storing depends on how it is going to be found, and separating them means optimizing each against a fixed guess about the other. The argument against it is equally real, and it is the mirror of what made Axis 1 clean. Once both halves move, you can no longer say which half produced a gain. Which of those 2 arguments you find more persuasive determines which axis you should be reading. Training runs in 3 progressive stages with stepwise optimization, rather than one reward at the end of a trajectory. What staging buys is a path into an action space too large to explore from a cold start, you widen the control the policy has as it becomes competent with what it already had. What it costs is that the curriculum has become a hyperparameter, and a badly chosen curriculum is indistinguishable from a badly chosen policy when you look at the final number. I am deliberately not putting results on this slide. Our verified record for this system covers its structure and not its measurements, and I would rather leave a visible gap than fill it from memory. Third axis, and this one completes the picture. MEMCON learns the read decisions, when to retrieve, what to retrieve, how much of it, when to inject a distilled plan, and when to merge or forget. The right path is left alone. It models memory operations as a decision process, like the other two, but the decisions it actually takes are retrieval decisions. And the structural point, which matters more than the method, it sits outside the memory system rather than inside the agent. Because it wraps rather than replaces, it composes with every one of the four architectures we read last episode instead of competing with them. It is also the axis that our first plan for this episode had missed entirely, which is worth admitting. And it is thin by construction, which is the part one would most want an engineer to take away. It is back-end agnostic, it does not need to know which memory system it is wrapping. The learner is a tabular contextual bandit with an upper confidence bound rule, not a language model being fine-tuned, a bandit over a discrete decision. There is no pre-training, there are no additional model calls, and it converges within dozens of tasks. Now hold that against the price strip on slide 12. Same problem family, and the training budgets differ by orders of magnitude. That gap is the most practically important thing in this episode. A bandit over a discrete decision is a very different engineering commitment from a fine-tuned policy. The reported result is up to 15.2 points of task success while cutting tokens by 5 to 20% across 6 benchmarks, 3 agent frameworks and 3 backbone models. The combination is the unusual part. Most memory work buys accuracy by spending context and pays for it in tokens, so a method that moves both in the good direction is telling you something diagnostic rather than just scoring well. It says the baseline was retrieving badly rather than retrieving too little. And notice the shape of the sweep, 3 frameworks and 3 backbones is what makes this a claim about the method rather than a claim about one stack. Here are the 3 run side by side on one observation stream. Axis 1 writes selectively and reads with a fixed retriever, so its store is sparse and heavily edited. Axis 2 changes both, so the store and the reads co-adapt and it ends up dense and reordered. Axis 3 leaves the store to whatever host it is wrapping, so its contents match the reference, but what gets pulled out of it is completely different. Watch the divergence, because the point is not that one track looks better. By the end of the stream these 3 stores are not variants of one another. They are different objects, produced by optimizing different things. So here is the grid, and here is the finding. Write, retrieve, update, forget and consolidate each have at least one claimant in this literature. The index row is empty across all 3 systems. Nobody is learning how memory gets addressed, only what goes in, what comes out, and what gets thrown away. And one distinction on this slide matters more than it looks, there is a difference between a dash and the phrase frozen by design. A dash is a gap nobody has filled. Frozen by design is a deliberate methodological choice that bought Axis 1 the ability to attribute its own results. Do not read them as the same cell. 3 controllers, 3 axes, and the comparison is less flattering to learning than the papers make it look. Marginal cost per decision, a rule is near 0, a judge is a full model call, a learned policy is one forward pass, so learning wins there, decisively and often overlooked. Auditability, a rule is completely auditable because you read it, a judge gives you a rationale you cannot rederive, and a policy gives you a number you cannot interrogate at all. Cost to change the behavior, edit one line, edit a prompt, or retrain. A learned policy wins the first row and loses the third, and whether that trade is worth it depends on how often your policy has to change. One more empirical result, from the same study episode 3 used for a different finding. Local maintenance is more cost-effective than global reorganization, measured across 12 memory systems and 2 baselines, 5 workload classes and 11 datasets. Notice that every action space in this episode is a set of local edits, so that shape now has support independent of any one system. And it gives a reason for the empty index row. An index is the global structure, and rebuilding it is precisely the operation this result tells you to avoid. The engineering reading is direct. Prefer small reversible edits to a policy that periodically reorganizes everything. 2 findings from one study, in 2 different episodes, and neither of them is about a system we have named. One more design, because it separates something the others leave fused. e04 runs 2 stages. The first induces guidelines. Contrastive feedback produces an explicit statement of what a good memory entry should look like. The second optimizes a policy against structured process rewards, aligned to those guidelines. What has been separated there is the policy over operations from the representation being written, and that separation is what makes the ablation interpretable, because you can change one and hold the other. In every other system on this axis, a change in the reward changes both at once and you cannot tell which moved. That is a small methodological point with a large consequence. Interpretability of the ablation is a property of the design, not of the write-up. And that first stage is worth naming precisely, because of where the idea comes from. The contrastive feedback is a textual gradient, a critique written in natural language and then used the way a gradient is used. That concept is not from the memory literature at all. It comes from the optimization line we take up in episode 7. So a memory control method is already running on machinery from the self-evolution half of this series. This is the first place where these 2 segments of the spine genuinely touch, and I want to be clear that it is not a transition I invented for the sake of the running order. The citation is in the paper. That brings us to a methodological point I want to make carefully. Learning a memory policy is a natural fit for offline reinforcement learning, and the reason is structural rather than fashionable. Online learning requires the ability to try a decision and see what happens, and in a live memory system a bad write is not undoable and the user on the other end is real. Offline learning takes recorded trajectories and never interacts with the environment while it learns. And memory logs are close to an ideal offline dataset, recorded decisions, observable downstream outcomes, no ability to rerun history. If you keep write logs at all, you already have the data. And here is where it fails, in 4 ways that you will meet in that order. Distribution shift, the agent's own writes change the store, which changes the states the policy will later encounter. Non-stationarity, what deserved storing last quarter does not this quarter, so the optimal policy moves while you are estimating it. Catastrophic overwrite, a retrained policy can be worse than the one it replaced, and the store it inherits was built by the old one. And the 4th, which is the deep one, the log never contains the writes a better policy would have made. You cannot learn from a decision that nobody took. Which means an offline dataset can only ever teach you to imitate the taste that produced it. Lab 4. Take one write log, the one Lab 3 asked you to instrument will do. Replay it against 3 eviction policies, a fixed budget, least recently used, and lowest predicted reuse. Plot read hit rate against storage held, and then look for the policy that wins on hit rate and loses on total cost, because that one exists more often than not. 30 lines or so against the claims triage corpus in the repository. This is the cheapest possible version of the experiment the entire episode is about, and in my experience the answer is not the policy you would have guessed. If the plot surprises you, that surprise is the same one every paper in this episode is written to resolve, and you got to it in 30 lines. 5 takeaways. Memory management is a sequential decision problem, and the design choice that matters is the action space rather than the algorithm. The signal is sparse, delayed and a proxy, and every method here is a response to one of those 3. 3 positions exist: learn the right side, learn both, or learn the read side from outside, and they are different in kind rather than in degree. Nobody learns the index, and the local versus global result suggests that is defensible rather than an oversight. And training budgets for the same problem family differ by orders of magnitude, so ask for the price. Next episode, what happens to all of this as it ages?